Hi there, Mr. Sutton here, bringing you the AB Calculus 413 homework solutions on motion extra practice. For this free response problem, we have two runners, A and B, running on a straight race track between 0 and 10 seconds. The graph up here shows the velocity in meters per second of runner A, and then the velocity of runner B, also in meters per second, is going to be given by this v of t function. So part A of this problem, they want us to find the velocity of runner A and runner B at time 2 and have the right units of measure there. So for runner A, they didn't actually give us a formula, but they want the velocity at time 2. So velocity at time 2, we basically need to come up with a formula for the velocity and then plug 2 into it. Since the velocity between 0 and 3 is just this slanted line, we just need to write something in y equals mx plus b form. We'll have a y-intercept of 0 here, so we really just need to know the slope. We're going up 10 and over 3, so that's a slope of 10/3. So I can write this velocity from A to B as 10/3 times t. And then if I just plug in 2 to that, I'll have 10 over 3 times 2, which is just 20 over 3. And the units for that is going to be, since it's velocity, we're going to have meters per second. Next, I want my velocity of runner B at time 2. So in order to get that, I'm just going to use this v formula here. So I'll just do v of 2, and I can plug it right in there. If I wanted to, this is a calculator question, so I could just plug it in the calculator. Let me actually go and do that. So here I am on Desmos. Let me just write out this v of t function. I have a feeling I'm going to need to use it later anyway. So that's going to be 24t over 2t plus 3. And if I just plug 2 into that, v of 2 comes out to about 6.857, and that will also be meters per second. For part B of this problem, they want us to find the acceleration of runners A and B at time 2 with units of measure. So in both cases, I'm going to be taking the derivative of velocity and plugging in 2 to find the acceleration at that time. So let me just officially say here for runner A, we've got, again, we had the velocity of runner A was 10/3 t. That was from part A that we did that. The acceleration is just going to be v sub A prime of t. So basically just need to take the derivative of this and plug in 2. Well, the derivative of 10/3 t is just 10/3, and that'll be meters per second squared if I'm doing acceleration. It's going to be whatever the velocity units were divided by a time unit. That gives us the rate of change of velocity. All right, so next up for runner B, for this one I just need to take the derivative of this velocity formula that they gave us and plug 2 into that. And I don't actually need to figure it out algebraically. Since I'm just plugging in a single value, I can do this entirely on the calculator. So let me go back to Desmos, and let me just go down to new entry level, and I'm just going to do v prime of 2. This will give us the acceleration, which is about 1.469, and again, that's going to be meters per second squared. For this free response problem, for times 0 to 6, we have a particle moving along the x-axis, and the position is not explicitly given, but we're calling it x of t. The velocity is given by this v of t function. Looks like we've got some trig and exponential hybrid sort of thing going on. And they also gave us the acceleration with this a of t function. Now, keep in mind, we could have taken the derivative of v, and algebraically it would have given us this a of t. They just saved us the trouble of actually doing that derivative, which was nice of them. So for part A, they want to know, is the speed of the particle increasing or decreasing at time 5.5? Give a reason. So if we want to figure out if we're speeding up or slowing down, we need to figure out the velocity and the acceleration at 5.5, whatever units of time this is. And we need to compare those to see if they have the same sign or opposite signs. If the signs agree, then we're speeding up. If the signs are opposite, then we're slowing down. So let's first do v of 5.5, and I'm going to plug all this into Desmos. So let me write out my v function first. So that'll be 2 sine parentheses e exponent t divided by 4 and close the parentheses. All of that plus 1. And while I'm at it, let me just put my a of t in here. So I could just use v prime of t to get me values of a at any point I want, but maybe I'll need this later, who knows. So let me just put it in here. So we've got e exponent t divided by 4, come down to non-exponent land. We've got cosine, parentheses, e to the, again, t over 4. And that should do it. All right, so let's find v of 5.5. And it looks like that's coming out to negative 0.453. Now let's find a of 5.5 and see if that agrees. So let me just change this v to an a, and that comes out to negative 1.359. Since the signs of velocity and acceleration are the same, they're both negative in this case, that's telling us that the particle is increasing in speed. So since a and v have the same sign, particle is speeding up at time 5.5.
For number 3, we've got a car traveling on a straight road, and for part A, all we really need to know is that the acceleration of that car between 0 and 18 seconds is in the graph. So we want to know, based off of this, if the velocity of the car is increasing at t equals 2 seconds. The key to this one is understanding that acceleration, which we've graphed here, is the rate of change of velocity. If that's the case, that means that wherever acceleration is positive, the velocity must be going up, increasing. So we just have to see if acceleration is positive or negative at t equals 2. Looking at our graph, acceleration definitely positive. Since a of 2 is greater than 0, this is our justification now, that means the velocity must be increasing. So you need to put in both things here. You need to show that you understand acceleration is velocity's rate of change, and you need to show that when you plug 2 into that function, you get a positive, giving you this conclusion. For number 4, we have a car traveling on a straight road, and from 0 to 24 seconds, our velocity in meters per second, which is important because they're going to want units later, is modeled by this linear piecewise function. Now, piecewise linear, which they spelled out here, means we know for certain that each of these pieces is a line, which will also be important in the question we're doing. So we want to find v prime of 4 and v prime of 20, or explain why it doesn't exist. Starting with v prime 4, since we already have the graph of v prime is talking about the slope of that graph, and at 4, at t equals 4, well, we don't know the slope because this is a corner. It's a non-differentiable spot. So v prime of 4 doesn't exist because there's a corner at that value. Okay, how about v prime of 20? So 20 is up here. This is this spot right here we want to find the slope of. Since this is in the middle of one of those linear pieces, if we find the slope of this line, and we have 2 points, so we can find the slope, that will tell us what v prime of 20 is. So using our slope formula, we're going to do y2 minus y1. So that's going to be 0 minus 20 for the y values. And then for the x values, we've got 24 minus 16. So that's negative 20 over 8. Now, you actually could have stopped right at this point and put on units of measure and been done. But just to simplify it for the sake of simplifying, we've got negative 2.5, and then units of measure. If we want to know the rate at which velocity is changing, that's acceleration. That will be meters per second, or meters per second squared. For part C of number 4, let a of t be the car's acceleration. For 0 to 24, write a piecewise defined function for a of t. So we're essentially trying to write a function for the slope of this graph up here. So to do this, we just have to calculate, since these are lines, we just need to figure out the slope of each line, and we also have to find the intervals. How about the border values? We have border values of 4, 16, and 24, and at these border values, since we have abrupt slope changes, we're not going to include the border values at all. So all of our intervals that we're doing in our piecewise function are just going to be less thans. There's going to be no less than or equals. So those slopes then, for our first one from 0 to 4, we have a slope of, let's see, we're going up 20 over 4, so that's a slope of 5. Next interval, we've got a slope of 0 going from 4 to 16. And finally, we had a slope of negative 2.5 that we just calculated going from 16 to 24. So 5 from 0 to 4, 0 from 4 to 16, and negative 2.5 from 16 to 24. For part D of this one, we want to find the average rate of change of v over the interval 8 to 20. And there's some other stuff here, but let's do this piece first. So that means we're going to be doing v of 20 minus v of 8 over 20 minus 8. And we have a graph that tells us v values. So v of 20 right here, this looks to be 10. I mean, you could calculate it precisely, but it is 10. We have a slope of negative 2.5. So if I take 4 steps to the right, that means I'm taking 10 steps down. So we are at 10. And then v of 8 over here, that was on that horizontal line, that was 20. So we've got 10 minus 20 over 12. And you could just leave it like this and put units of measure. If you really want to simplify it down, you've got negative 10 over 12 or negative 5 over 6. Meters per second squared, that part has to go on there. Next part of the question, does the mean value theorem guarantee a value of c between 8 and 20 such that v prime of c equals this average rate of change? Why or why not? So for mean value theorem to apply, mean value theorem again says that a rock equals I rock somewhere on an interval if that interval is differentiable. So we have to figure out if we have a differentiable interval here. From 8 to 20, we have this non-differentiable piece at t equals 16. So the MVT cannot guarantee anything because v is not differentiable on that whole interval. Again, that corner at t equals 16. For number 5, we have Karen riding her bike on a straight road from home to school, starting at home at time 0 and arriving at school at 12 minutes. During this interval, her velocity is graphed here in this graph here, and that's in miles per minute. And it's a piecewise linear function, so we're guaranteed that all of these different pieces are, in fact, just regular lines. All right, part A. We want to find the acceleration of Karen's bicycle at 7.5 minutes. And you give units of measure. So 7.5 minutes, that's right here. Since that is on one of these lines, we just have to find the slope of this line because we know that acceleration is just the derivative of velocity. So if we find the slope of this line, we've got our answer. So we've got, let's see here, this is going to be 0.2 minus 0.3 for the y values and 8 minus 7 for the x or the t values. And you actually could leave it like this and put units of measure and be done. If you want to risk it, we can simplify it down. This is going to be negative 0.1 over 1, so negative 0.1. And the units on this is going to be, let's see, the velocity was in units of, they said miles per minute, so this is going to be miles per minute squared. For part C of this problem, shortly after leaving home, Karen realizes she left her calculus homework at home. Oh no, Karen! And she returns to get it. At what time does she turn around to go back home? Give a reason for your answer. The key on this problem is realizing that the velocity graph here, the sign of the velocity, is telling us the direction that Karen is going. When the velocity is positive, like most of this graph here, Karen is heading towards school. When velocity is negative, like down here, Karen is heading back home. So we know that Karen is going backwards on the road back home when that velocity is negative. That means that when velocity changes from positive to negative, like at t equals 2 minutes, that's the time that Karen must have turned around. So she was heading towards school, she started slowing down, realizing she left her homework at home, turned around at this time and started going back home, and eventually got there, and then this is when she's heading towards school again. For number 6, we have a rocket with a positive velocity after being launched from an initial height of 0 at time 0. The velocity of this rocket is recorded in the table here at selected values. We want the average acceleration of this rocket over the interval from 0 to 8, and then with units of measure. So average acceleration, that's going to be the average rate of change of velocity. So we're essentially asking for the AROC of this tabular function here. So before we actually plug in specific values, I'm going to write v of 80 minus v of 0 over 80 minus 0. And I'm doing this because I want to show the reader where the values that I'm about to plug in here are coming from. So now that I've done that, I can write in 49 minus 5 over 80 minus 0. And you could stick on units of measure, which is going to be feet per second, or feet per second squared, and actually be done. Or if you want to risk it, you could simplify this. This would be 44 over 80, which would be 11 over 20 if you reduce it. So 11 over 20 feet per second squared, the most reduced answer here. For number 7, we have the graph of velocity in feet per seconds of a car traveling on a straight road from 0 to 50, and that's in seconds. So we have a table of values at 5-second intervals, and we have a graph. So different representations here. So now part A wants to know during what intervals of time is the acceleration of the car positive, and give a reason for the answer. This is a graph of velocity. Acceleration, that's the rate of change of velocity. So whenever acceleration is positive, that means that our car's velocity must be increasing. So one part of our answer is really just writing out that we understand that. We can say a of t is positive or greater than 0 when v of t's slope is positive, because a of t equals v prime of t. And then the other part of the answer is actually figuring out where that happens. Well, we have a positive slope for velocity between 0 and all the way over here at 35. This is our turnaround spot. And also we have another one from 45 to 50. So those are our two intervals where we have positive acceleration because our velocity is increasing. For part B, they want average acceleration of the car from 0 to 50 seconds. So for this one, we're just asking for the average rate of change in velocity. So we can do v of 50 minus v of 0 over 50 minus 0. So we're going to write this out first so that people know where our numbers that we put in are coming from. But now that we've written this, we can write 72 minus 0 over 50. And then you could just stick feet per second squared after this and call it a day. It was a calculator question, so if you wanted to, you could divide this and get 1.44 feet per second squared. But as long as you had the units, you didn't actually need to take this extra step. For part C, they want one approximation for the acceleration of the car at time 40 and then show the computations you used. So since we don't know the actual formula for this, we can only approximate by taking the average rate of change over an interval. So how about we just find the average rate of change over an interval that includes time 40? Probably the best interval to use would be 35 to 45. And if you look up here, 40 is, somewhere on that interval from 35 to 45. So that looks like a pretty good approximation there. So let's do then v of 45 minus v of 35 over 45 minus 35. So that's going to be 60 minus 81 over 10. And let's see, that's negative 21 over 10. You could reduce it if you wanted to negative 2.1 feet per second squared. But honestly, you could have stopped at this point here where you plug the numbers in and just stuck the units on.